Okay, let's evaluate the limit as x approaches 0, x minus 4 sine x over x squared minus 16. So normally the first step we want to take is to plug in 0. And that would look like this. The limit as x approaches 0, 0 minus 4 sine 0 over 0 squared minus 16. So sine 0 will always give us 0. And then over here you have 0 minus 4, which would give us negative 4, but times that 0, we would get 0. And on the bottom right here, 0 squared would give us 0, minus 16 would leave us with negative 16. And 0 divided by negative 16 would give us 0. So that would be our final answer. Next, we'll evaluate the limit as x approaches 4, x squared minus 4x over x squared minus 16. So we'll have the limit as x approaches 4. And up here, we'll just factor out an x, which would leave us with x times x minus 4. And on the bottom here, x squared minus 16 is equivalent to x plus 4 times x minus 4. And if we multiply it together, we'll just end up right back here. But this just makes it easier to work with because then we can get rid of the x minus 4 up here and the x minus 4 down there, which would leave us with the limit as x approaches 4, x over x plus 4. And there's nothing left to do, so we can go ahead and plug in f4 for anywhere we see an x, which would leave us with 4 over 4 plus 4, which would give us 4 over 8, which would equal 1/2. And this would be our final answer for this one. Okay, for this next example, we'll evaluate the limit as x approaches negative infinity, x cubed plus 3x over 4x squared minus x. And for this problem, we can use something called the dominant term rule, which will only ever be applicable if x is approaching either negative infinity or positive infinity. And basically, we'll only focus on the terms with the highest exponents. So up here, the term with the highest exponent is x cubed, and in the denominator, the term with the highest exponent is 4x squared. And any other term you can just ignore. So what we're left with is the limit as x approaches negative infinity, x cubed over 4x squared. And remember, this will only ever be applicable if the limit is approaching negative infinity or positive infinity. So up here we can take out 2 x's, which would leave us with just x, and down here you can take out 2 x's, which will leave us with just 4. So what we're left with is the limit as x approaches negative infinity, x over 4. And if we plug in negative infinity for anywhere we have an x, we'll be left with negative infinity over 4. And negative infinity is just so big that even if you divide it by 4, you'll still be left with negative infinity. So this will be our answer for this one. Okay, for this next example, we'll evaluate the limit as x approaches 0, the absolute value of x over x cubed plus 3x. And what we're going to do first is simplify this denominator a bit more by bringing out an x. So then it will look like this. The limit as x approaches 0, the absolute value of x over x times x squared plus 3. And then we're just going to divide it into 2 parts, so it's going to look like this. The limit as x approaches 0 the absolute value of x over x times 1 over, x squared plus 3. We just separated it into two parts. So first, let's focus on this term right here. So the absolute value of x over x will equal 1 if x is bigger than 0. And it will equal negative 1 if x is smaller than 0. So those are our only two options, so we're going to evaluate our original limit once with a positive 1 and once with a negative 1. So let's start first with the negative 1. The limit as x approaches 0, positive 1 times 1 over x squared plus 3. And if we go ahead and plug in a 0 for anywhere we have an x, that will look like this. The limit as x approaches 0, positive 1 over 1, positive 1 times 1 over 0 squared plus 3. And that will leave us with 1/3. So that's our answer to the limit if we use a positive 1. So now, with a negative 1, we'll have the limit as x approaches 0, negative 1 times 1 over x squared plus 3. And again, if we plug in a 0 for anywhere we have an x, we'll be left with the limit as x approaches 0, negative 1 over 0 squared plus 3, and that will give us negative 1/3. So again, this one is for when we use a positive 1, and here is when we use a negative 1. And because 1/3 is not equal to negative 1/3, for this limit, the limit does not exist. That will be our final answer. So for this example, we have the limit as x approaches 0, x over 4 minus the square root of x plus 16. So what we're going to do to work through this is first to rationalize the denominator. So that's going to look like this. The limit as x approaches 0, x over 4 minus the square root of x plus 16 times by 4 plus the square root of x plus 16 over the same thing, 4 plus the square root of x plus 16. And that's going to leave us with the limit as x approaches 0, x times 4 plus the square root of x plus 16, and the denominator will have 16 minus x plus 16. So then we're going to simplify this right here. So 16 minus x minus 16, and the negative 16 will get rid of this positive 16, so we'll be left only with a negative x. So we're left with the limit as x approaches 0, x times 4 plus the square root of x plus 16 over negative x. And this x will get rid of this x, but remember we'll still have this negative. So this will all simplify to the limit as x approaches 0, negative 4 plus the square root of x plus 16. So then our next step is going to be to plug in this 0 anywhere we see an x. So we'll have the limit as x approaches 0, -4, parentheses right here, 4 plus the square root of 0 plus 16. And that'll simplify down a bit more to limit as x approaches 0, -4 plus the square root of 16, and that'll simplify down to -4 plus 4, which would be -8. So the -8 is going to be our final answer right here. Okay, this example is going to be similar to the previous one, and we'll approach it again by rationalizing first. So that'll look like this. The limit as x approaches 4, the square root of x minus 2 over x minus 4. And to rationalize, we're going to have to times it by the square root of x plus 2 over the square root of x plus 2. And that will look like this. The limit as x approaches 4, the square root of x minus 2 times the square root of x plus 2 over x minus 4 times x plus 2. And if you work out the math up here and down here, you'll end up with this. The limit as x approaches 4. On the top, you'll get x minus 4, and on the bottom, you'll get x minus 4 times the square root of x plus 2. And maybe you can already see it, but this one will cancel out this one down here. So what we'll be left with is the limit as x approaches 4, 1 over the square root of x plus 2. So then our next step is to plug in a 4 anywhere we have an x. So what we'll be left with is the limit as x approaches 4, 1 over the square root of 4 plus 2, which would be 1 over 2 plus 2, which would be 1/4. And that will be our final answer for this question. Alright, for this final example, we have the limit. We'll evaluate the limit as x approaches 0, 9 plus x squared minus 81 over x. So our first steps will be to expand this right here. And that will look like this. The limit as x approaches 0, 81 plus 18x plus x squared minus 81 over x. So everything you see underlined right here is what 9 plus x squared used to be. I just expanded that squared. So maybe you can already tell, but this 81 will cancel out with the -81, and we'll be left with the limit as x approaches 0, 18x plus x squared over x. And because they share an x, we can go ahead and factor out 1x, which will leave us with the limit as x approaches 0, x times 18 plus x over x. These two x's will cancel out, leaving us with the limit as x approaches 0, 18 plus x. And then if we plug in a 0 anywhere we have an x, we'll be left with 18 plus 0, which would just equal 18. So our answer for this example is 18.